Last lesson we saw two failures, a model too simple and a model too complex. Those failures have proper names, bias and variance, and there's a beautiful way to picture them. Imagine throwing darts. Here's a dartboard. The bullseye in the center is the true answer we're trying to hit. Now, each dart is one model, trained on one particular sample of data. If we gather data again, we'd get a slightly different sample, and a slightly different model, another dart. Where the darts land tells us everything. First, bias. Look at these darts, tightly grouped, but landing well off to one side, far from the bullseye. The model is consistent, but consistently wrong. It's making a bad assumption about the shape of the data, like forcing a straight line onto a curve. That systematic miss is high bias. Now, variance. This time the darts are centered on the bullseye on average, but they're scattered all over the board. The model is far too sensitive to the exact training sample it saw. Change the data a little, and the prediction jumps somewhere new. That instability is high variance. Put them together and we get four cases. Low bias and low variance, tight on the bullseye, is the dream. High bias is off target, high variance is scattered, and the worst case is both at once. Real models live somewhere on this grid, and our job is to push toward that top left corner. This maps straight onto last lesson. Underfitting, the too simple straight line, is high bias. It's systematically wrong, no matter which data you give it. Overfitting, the wiggly curve, is high variance. It reshapes itself wildly for every new sample. Here's the tension. As we make a model more complex, its bias goes down. It can bend to fit the pattern, but its variance goes up. It starts chasing the noise. Your total error is roughly the bias plus the variance. One falls while the other rises. So the total forms that familiar U-shape, and the best model sits at the bottom. This is the bias-variance trade-off. So, bias is being consistently wrong, variance is being unstable, and good models balance the two. But this raises a question. To balance them, we need to measure a model's true error honestly. That starts with knowing what score is even worth beating, a baseline. That's next.